Hello everyone, welcome to this video. In this video we shall be seeing the scaling property. So first of all we should understand what is scaling. So scaling basically is a operator. So I can say scaling is an operation which is being performed onto some given function or signal. So let us understand this in this way. Suppose you are given this function or signal as f of t. What you do? You apply the operation of scaling onto this. So as a result, you will obtain the same function where this variable now has been adjusted or multiplied by some constant a, where depending upon this constant, if this constant is less than equal to 1, we have expansion, and if a is greater than 1, then we have compression. So that means if we apply this kind of operation, then your function or signal, in this case, that expands. So suppose your original signal was this one, so in this case it now becomes something like this. And in the second case, with the compression, suppose your original signal was this, then what does what happens to this signal? So it shrinks or it compresses. So accordingly we have this scaling operation. So to understand it in a more better way, let me give you an example. So suppose your given function is this one, f of t, which is defined to be piecewise continuous function having the value as 2 in the domain -2 to 2 and the value 0 otherwise. So this is your function. So how does it look like? So let me draw it. This is the real line, right? So here this axis represents your variable t, this is minus t, and you can have this vertical axis where this represents the function's value. Suppose this point is 2, this point is -2, this point is also 2, then within the interval -2 to 2 your function has the value as 2, right? Obviously it would be a straight line, and otherwise its value is 0, right? So this value is this and this is the value. So this is the function that is given to you. So you may join this in order to represent that you have a discontinuity here at this particular point, right? So this is your function. Now what I am doing here in the first case, so I am discussing case 1, where I am multiplying this variable t with a, which is 1 by 2, right? So I have to define another function f of t by 2. So what would be this? It would be the same function, but now the interval changes. Instead of this -2 to 2, now instead of this t, we are now having the value as t by 2. So this would be your interval. So finally when you remove this 2 from here, so you have -4 to 4. So that means you can see that your interval now changes from -4 to 4 and it is 0 otherwise. So this is your expanded function when you multiply this given t by 1 by 2, which is less than 1, right? So your function would now look like this. This is minus t, this is t, this is the function's axis over here, right? And the value here is 2, the value here is -4, and here it is 4. So in between -4 and 4 your function's value is equal to 2, right? Obviously this is a straight line, and otherwise at all other points its value is 0. So that means this is your function. So you can clearly see that it has been expanded when you multiply by a factor of 1 by 2, which is less than 1. In a similar way, we can, in case 2, discuss about compression. So when you compress some function, so that means you are multiplying by some constant which is greater than 1, right? So this constant is obviously greater than 1, so I'm saying let the constant a be equal to 2, right? So when it is equal to 2, then your function would become f of 2t. So that means the function's value 2 and 0 would be the same, but now the interval would change. Earlier the interval was between the points -2 to 2. Now within the same limits, we, instead of t, we are now having 2t. So it would be -2 to 2, the value is 2t. So therefore when you solve this and you reduce this again to t, so this would become this. So with that means when you divide by divide by 2 on both sides, this would be your limit. So that means whenever t lies between -1 to 1, your function's value is equal to 2 and it is 0 otherwise, right? So this is how you convert the limit. So when you draw this particular function, this is your time axis and this is your function's axis. Therefore between the limits -1 to 1, the function's value is 2, and otherwise at all other points its value is equal to 0. So you can clearly see that this function has now been, the original function has now been compressed, so by applying this operation. So after getting to know about the scaling function, let us now see how this scaling could be beneficial in case of Fourier transform. So that was our main question that we intended to see, right? So we wanted to check what is the effect of scaling under Fourier transform. So to see the effect of this, we have a property which says that, so we have a property which states that if the Fourier transform of some function f of t is defined by capital F of omega and a is any real number, then the Fourier transform of f of at, that would be equal to 1 by a capital F of omega by a. And in a similar manner, we can also define this property in the reverse direction. So in the inverse sense, so it would be the Fourier inverse of capital F of omega by a. This is equal to a into small f of a t. So these are the two important properties that relates the Fourier transform and inverse Fourier transforms whenever the functions are being scaled. So now you might think that what is the use of this particular property? So question here is that what is the use? So you can clearly see that if you have already calculated the Fourier transform of some typical function f of t and you already know it is equal to capital F of omega. So now you have some another function which has just been scaled by a or 1 by a. So that means in that case, do you have to repeat your calculations with this transformed or scaled function? The answer is no. You can use this property and you could make use of these relations. So that means whatever result you have after the application of this unscaled version of the function, you just replace this omega by a in the first case, or by or in the inverse case, if you already know what is the inverse Fourier transform of the function, we can also say inverse Fourier transform of the function f of omega, this is equal to f of t. So if you already know the Fourier inverse of capital F of omega, in that case we can replace this t by at. So that is what is the use. Okay, so now it's time to prove the property. So for the proof of this property, we are starting with this quantity, so the left hand side. So here our left hand side is the Fourier transform of f of at, right? So we can apply the definition of Fourier transform here. So according to definition of Fourier transform, it is the integration from minus infinity to infinity, whatever function you have, e to the power minus iota omega naught t dt, right? And the function we have is f of a t. This is our function. Now we wanted to convert this function into that of f of t, right? So we wanted to remove this factor from here. So what I can do here, I can substitute this at as some other variable, say tau, so that when you differentiate it, now a is constant, so its derivative would only be with respect to t, so this thing would be there. And moreover, the limits, whenever your t is approaching to minus infinity, that implies tau also approaches to minus infinity according to this relation, and whenever t approaches to plus infinity, that implies tau also approaches to plus infinity. So that means the limits are going to remain the same over here. So we can now make this substitution. So when you substitute the quantities, so you have this thing as equal to integration minus infinity to infinity. In place of at we are writing tau, right? So e to the power minus iota omega naught. Instead of t we are writing tau by a, and in place of dt we are writing d tau by a, right? So now what we can do, so this is a term after substitution. So now I can take this a outside, so it would be integration from minus infinity to infinity f of tau e to the power minus iota. Now this I can also rearrange this like this, omega naught by a into tau d tau. So now if you compare this whole quantity with that of Fourier transform, so let me write down the definition again. So according to the definition of Fourier transform, so you have the Fourier transform of some function f of t as integration from minus infinity to infinity f of t e to the power minus iota omega naught t dt. So that means, and you write this whole thing as capital F of omega, right? So that means omega naught here. So that means whatever is this variable here, you write that in place of omega naught. So similarly, this definition resembles this definition where t is this variable for integration. Here our variable is tau. So that means 1 by a would be as such. This whole thing could now be written as capital F of this factor, so which is omega naught by a. So that means we reach to our right hand side, right? So we have used this definition of Fourier transform in order to reach here. So we have our right hand side as this one, 1 by a f of omega by a, right? So that means we have proved our result in this particular case. Next, we also have one more property, which is the special case of this property. So here this property is known as the reversal or the folding property. Which is also known as reversal property. So This case is applicable whenever the variable or the constant a is equal to -1, right? Whenever a is equal to -1, then our property becomes that Fourier transform of f of minus t. So that means we have now multiplied by -1 here, so a is -1. This is equal to capital F of minus omega. So this is the property that we have. So for an example, what is this reversal property? Or so I can give you one example here. So suppose we have unit step function. Now what is that? It is the function which is defined usually by u of t, right, whose value is equal to 1 whenever t is greater than equal to 0 and 0 otherwise. So this is your unit step function. How does it look like? So we have this as the function's axis, which is u of t, and this as the t axis. This is plus t and this is minus t, right? This is 0 here. So whenever t is greater than equal to 0, the function's value is 1. So here we have 1 and here we have 0. So this is our function. So here this is your function u of t. Now what I am doing, I am just taking this function. So that means in place of t I am replacing minus t, or you can also say I am multiplying this t by a. So you have u of minus t. So what would this become? This would be, so in place of t, now you have minus t. So earlier the limits were these, now you have the limits as minus t greater than equal to 0. So in other words, you can say t less than equal to 0, right? So your limits here, they become, according to this, they become t less than equal to 0 and 0 otherwise. So that means when you draw this function over here, this is the function's axis, this is the time axis, right? Here whenever t is less than equal to 0, the function's value is equal to 1. So this is 1 here, and otherwise the function's value is 0. So when you look at this function, this is what? This is u of minus t, and this function, this is u of t. So when you make a comparison among these two, you can see that one is the mirror image of other when you put the mirror in the vertical direction. So this property, that means whenever you are multiplying by a is equal to -1, you are having the reversal property. So whenever some function exhibit this reversal or folding property, we can make use of this property, which relates the Fourier transform of the original function with that of the reversed function, right? Well, that is it for this video. I hope you understood the concepts well. Thank you for watching.